Howdy folks, I'm really excited to start an analysis on a mineral sample that a friend sent to me. He actually sent me two samples, and the first one was a chemical salt that I analyzed in a couple previous videos to be manganese sulfate. But this one is actually a ground mineral, and he didn't tell me what it is, and he wants me to do a wet chemistry analysis on it, and so I'll go ahead and do that. He did give me some physical properties too. The specific gravity he said was 2.6 and the hardness was 2. Now if I had the actual rock rather than the mineral, the powder, I would actually do a fusion test on it too. And that tells you kind of what temperature the thing starts to melt, if it does at all. I have this reference called Mineral Tables. It's Hand Specimen Properties of 1500 Minerals by Richard Dietrich. And basically, with that information, I could kind of go by the color of the mineral, then it ranks it by the hardness, and then the specific gravity, and that should give me a kind of narrow it down. And then if I had the fusibility also, I could kind of narrow that down even further, even though that's not in this book. And before I do the wet chemistry, I think I'll do the same test that I did on the chemical salt. And I did a borax bead and a flame test, so I think I'll do that. And there's a couple other things I might try too, since I don't think I can do a fusibility on the powder, because I would blow the powder with the torch all over my lab bench or the hood. But I could do a closed tube heating and seeing what changes happen to the mineral itself, or if any gases or liquids come off, or if there's any sublimates that form on the outside of the tube. So that might give us some information. And the very first thing I'm going to do is look at it under a microscope and see if there's anything of note with maybe the way it fractures when it's being crushed, or color or anything like that. So anyways, I'm excited to give this a try. It's definitely going to be harder than the mineral salt, but I'm looking forward to it. Well, looking at it under the microscope was pretty fruitless. It just showed a white powder that was opaque, and it wasn't in any special shape. It was just kind of in globules and, you know, packed together. So the material is pretty soft, and it shows under the microscope. But anyways, I might include a picture, but really didn't gain any information from that one. I have a little bit of the mineral in the bottom of this test tube. The test tube's kind of deformed because I've done a closed tube test on it before, but I'm going to heat it to a pretty high temperature and look for any sublimates, condensates, or gases that might be given off. I have some pH paper that's wet that I can use to test the gas or condensates, and even lead acetate paper and a wood splint so I can check the gas to see if it supports combustion. I'm heating this fairly slowly. I've gotten this thing pretty hot, and I really haven't seen anything happen other than maybe a little bit of steam right at the beginning, which I don't know if that would really mean anything other than there might have been some humidity with the tube and the sample. But yeah, I don't see anything coming off. I don't see the sample itself changing, so that was pretty much a dead tube. The material at the bottom of the tube was quite basic in itself. Let's make us a blank borax bead. This is a platinum wire. That bead looks nice and clear. Alright, we got some mineral on there. Alright, I have quite a bit of mineral on there, and I don't see any color whatsoever. Our bead is really crystal clear, so the borax bead test was of no help. Okay, we're going to try that with some mineral. Whoa, we got a lot of orange there. And some red at the end there. A lot of orange. Now it's getting a little bit reddish. I don't know if you can see that. Now calcium is a kind of a orangish red, so that's looking like calcium to me. It could even be sodium. We're going to try some sodium as a comparison. because I'm not sure if it's sodium or calcium. Well, that's a similar color too, so it could be sodium. So when I analyzed the chemical salt last time, the borax bead pretty much gave us the answer. This time we got a clear bead, so that didn't really narrow it down to anything specific. It did rule out a few things that do give colored beads, but other than that, it didn't tell us what it was. The microscope was no help, nor was the closed tube. That didn't seem to do much either. What did seem to give us some information was the flame test this time. And that came out to be a bright, kind of a yellowish, orange, reddish. And I tried to go back with some known salts of both calcium and sodium. It was kind of hard for me to tell the difference, so I don't know why. We can't do too much more with the physical testing because we just have the material as a powder, but we could go through more classical testing. But that gets to be pretty involved. There's 3 different fluxes you can use. You can try it without a flux. You can use those fluxes on a charcoal tablet. You could use those fluxes on a or plaster tablet. And you can do those with reducing and oxidizing flames. So you go through that, and there's a million different combinations. So I don't even think I have enough sample to even come close to doing a bunch of those. And to top it all off, the results are kind of subjective when you start looking at color differences and colors of sublimates and stuff like that. So we're going to skip that, and we're going to go right into the wet chemistry now. So the first thing we have to do is to get the stuff in a solution and then go through our test procedure. The first thing that I did is kind of a screen, is I just put a little speck of the mineral on a watch glass here, and I added a drop of 10% hydrochloric acid, and I wanted to see if it will dissolve in hydrochloric, and it's actually fizzing, so that's indicative of a carbonate. And it also means that the mineral should dissolve in hydrochloric acid, so we can go right to dissolving it in hydrochloric acid, which will save us a step as far as testing for the silver cation group, because those cations actually don't dissolve in hydrochloric acid. So if it dissolves, we can rule those out and continue with the analysis. I like to use about 2/10 grams of the sample. I'm going to add that to a test tube. To that I'm going to add, maybe 2 or 3 mils of acid, hydrochloric acid. And you can see that is giving off quite a bit of gas. Alright, so that sure did dissolve completely. I'm going to add a couple mils of water just to bring the volume up to about 5 mils. I didn't do any testing on the gas. I wasn't really prepared, so if I want to look at the anion, I'll go back and revisit that. The Orsino-Smith book has a lot more cations that it tests for. We look at the rare earth group, which also has thallium and scandium in it. So we're going to take half of our stock solution here, and we're supposed to adjust the pH to about neutral with ammonium hydroxide, and then make it acidic again with hydrochloric, and then add some oxalic acid solution, saturated oxalic acid, and the rare earth group elements will precipitate out if they're there. That's near neutral with the ammonium hydroxide. Now we add 1 mil of acid back to it, and we'll dilute it down. The volume's supposed to be about 25 mils, which is quite a bit. Now we add 5 drops of concentrated oxalic acid solution. I heated that a couple times, and there's no precipitate, so there's nothing there from the rare earths group. I'm ready to go ahead and precipitate out the copper and the tin groups. In the Orsino-Smith book, the copper group includes copper, lead, cadmium, bismuth, palladium, rhodium, osmium, rhenium, and polonium. And the tin group includes tin, mercury, antimony, arsenic, molybdenum, scandium, tellurium, platinum, iridium, germanium, and ruthenium. Now before you do that, you're supposed to take what was left over from the rare earth analysis, dry it down, You're supposed to redissolve it in different reagents and then dry it and then ignite it and then add I think some more acid to it and dry it out again and add more acid to it again. And I'm not going to fool around with all that. For one, I don't want to use up all my reagents, but we still have half of our original solution, so we can go ahead and do that. Now the only thing we have to do to precipitate out the copper and tin groups is to adjust the pH to be to a certain acidity and then bubble hydrogen sulfide through it, and we're done. Now the last time that I did this on the salt, I was using a different reference, and they had me making a bunch of adjustments and bubbling hydrogen sulfide through 3 different times, or maybe even 4, and making adjustments in between there every time. So this is going to be a lot simpler. We're supposed to heat this actually before we bubble the hydrogen sulfide through it. We're heating the hydrogen sulfide generator, which produces the gas. It comes up through the tube and down into the solution where it bubbles through the solution. There's no precipitate, so there is nothing from the copper nor the tin group. To remove any remaining hydrogen sulfide so we can continue with the testing, we then heat to boiling. We're supposed to test for phosphate because it could cause some problems later in the analysis, and if it's not there, it simplifies things. So you take a drop of ammonium molybdate, a drop of concentrated nitric acid, and you're supposed to add those 2 first and mix it, and then a drop of sample. We don't see a yellow precipitate there, so there's no phosphate, so we don't have to worry about any weird interferences or anything. We didn't find any precipitate with the hydrogen sulfide, so there was nothing in the copper or tin groups. But now we're going to go ahead and test for the iron and aluminum groups. And the iron group contains iron, manganese, cobalt, nickel, and indium, while the aluminum group contains aluminum, zinc, chrome, beryllium, uranium, vanadium, and gallium. And continue with the testing. We need to make it alkaline with ammonium hydroxide. I've heated this to boiling, and I see a little bit of stuff floating in there. Kind of white, not much, and I have boiling stones in there because it wants to fly all over the place. Here's the ammonium sulfide. We're going to heat that back up. This is what we ended up with from the iron and aluminum precipitation. There's actually a very small amount of precipitate. It's kind of a light tan, whitish, brownish sort of material. We got a little bit of material from the iron and aluminum groups, but the next step is to precipitate out the calcium group from the filtrate. And that actually includes calcium, barium, strontium, and magnesium. And to do that, we need to reduce the volume down quite a bit, and then add ammonium carbonate in equal volume, and then an equal volume of 95% alcohol, and it doesn't say what kind. Right now we're reducing the volume down. I have the solution boiled down to about 1 ml, and we're supposed to add equal amounts of ammonium carbonate and alcohol, and look for a precipitate for the calcium group. Well, we got a precipitate even before the alcohol. We're supposed to let this sit with occasional agitation, but it looks like we have quite a precipitate already. Here's the calcium group after precipitating and centrifuging. And as you can see, that's quite significant. That's a lot of material. It wasn't like the little bit that we got from the iron and aluminum groups. Well, by the quantity of this material, I think we can pretty much assume what we saw in the flame test was calcium. In fact, according to Orsino Smith, his main confirmation test is to do a flame test, and the calcium should come up the yellow to orange red, the barium yellowish green, the strontium crimson red, and magnesium doesn't come up with a color. So we've already done that. Definitely had that strong yellowish to orange red. So I think we don't have to go any further. If we look at the sodium group here, there's not a lot of good confirmation tests for those either, and he basically refers you back to the flame tests for those also. So looks like we have calcium. There's one other confirmation test that we can try for the calcium group, and so let's give that a try. The one indicator that I know of that involves calcium is area chrome black T, and it gives an indication for both magnesium and calcium. It also involves a buffer. So I actually have a blank here, which is just water, a magnesium known, which is Epsom salts or magnesium sulfate, some calcium chloride, and then the sample. So we're going to add a drop of the buffer solution to each one of these. Give that a little bit of a jiggle. And now we're going to add the indicator. Now it's going to be a dark blue on its own, but it should turn kind of a reddish. Okay, there's the blank. And there's the magnesium, there's the calcium, and there's the sample. So we see definitely a blue color on the blank. And then the magnesium, calcium, and sample are showing, the reddish color. So those are showing positive. This isn't in the Orsino-Smith book either. But if you make the solution alkaline after the iron-aluminum groups, so this has the dissolved calcium, you should throw it down as a precipitate with ammonium oxalate. Actually, the magnesium should stay in solution. And sure enough, that's a pretty good precipitate. Well, that's another indication of calcium, and the fact that the calcium was precipitated out with the ammonium oxalate as a insoluble calcium oxalate. For the sake of completeness, there's one more step to do. As you see, we got the calcium group precipitated down here, but the liquid does contain the sodium group. And what they have you do in the Orsino-Smith book is to put that into a crucible, dry it out, and then ignite it. And if there's any residue left, that's the sodium group, if there's any present. So we'll go ahead and give that a try and see if there's anything there. Okay, we're getting the solution dried out. Now, as you can see, we're driving off the ammonia salts. There's not really much left in there at this point, but it's still smoking. Alright, I think we did everything we could to figure out the cation, and now we need to figure out the anion. And when we dissolved the mineral in hydrochloric acid and saw that it gave off gas, that's pretty indicative that it may be a carbonate. There could be other gases that could be given off too, but we're going to do a confirmation test for carbon dioxide. And to do that, we're going to take a little bit of our mineral, and we're going to add some hydrochloric acid back to it to form the gas. And then if you suspend a drop of either calcium hydroxide or barium hydroxide in the gas, it will turn cloudy. That's because it will form an insoluble barium carbonate or calcium carbonate. So we'll give that a try. Hopefully I won't drop the material into the test tube. I got the camera angle in kind of tight. We'll go ahead and add our acid. And sure enough, it's giving off some gas here. So kind of let that fill up the tube. And we'll try to suspend a drop of our hydroxide in the tube. Now I'm going to kind of depress it so the drop is kind of exposed. I've heard you can put a glass rod with a drop on the end of it and suspend it in here also. I sort of played around with that and I didn't have good luck. Alright, it looks like it's getting cloudy. Alright, let's see if I can get a dark background here for you. So you can definitely see that the drop is milky against the dark background. So that's the carbonate that is forming, that's insoluble and giving it a milky color. So that's indicative of a carbonate, and that it is carbon dioxide. So we know that the mineral is a carbonate. Here's a summary of our results. For the cation testing, we definitely saw quite a bit of calcium there, and we found 4 different indications that it was there. The first thing was the flame test, which gave us the kind of yellowish, reddish orange flame. We also saw quite a bit of material come out in the group calcium group precipitate, where we precipitated it out with the ammonium carbonate and the alcohol. So definitely a lot of material came out. So there's probably a a lot of calcium. We also used the area chrome black tea, and got an indication there, which gives us an indication for magnesium and calcium. And we also precipitated out some of the material as a precipitate in a alkaline medium, which is indicative of calcium. Actually, magnesium wouldn't precipitate out. The other thing that we found was a little bit of precipitate with the iron and aluminum groups, and it was just a trace, but it definitely seemed to be something there, but not enough to really worry about. But I'm going to take note of it because this mineral is supposedly not common, so I want all the information that I could get. And at the very end, we saw a little bit of material left over that could be from the sodium group, but it was very small, and I'll include it here as a possible trace because who knows, maybe there was some sodium that was included with the flame test, because that's kind of hard for me to at least differentiate between that and calcium. And the last thing is possibly magnesium. I don't have a good confirmation test for magnesium. In the Orsino-Smith book, he uses a material called quinalazarine, and I don't have it and haven't been able to find a source for it. There's also things that you can do to separate out the calcium from the magnesium, but it seemed like we got quite a bit of calcium out with the oxalate group, that magnesium could be there possible, but I'm kind of guessing that it's mostly calcium in any case. As far as the anion, we deduced that it was a carbonate, and there were two indications of that, and that was the hydrochloric acid fizz test and also the calcium or barium hydroxide test that forms that cloudy precipitate. The other information that was given to us is that it's not a common mineral, so that's kind of important, and actually all these are important. The hardness is less than 2, and the specific gravity is around 2.6. So let's give that some thought and look for some possible candidates. This is what we know for sure about the mineral. We don't know the formula, but we do know that there's definitely calcium in there, and we know that it's a carbonate, and the powder is a white color, so the streak is white. We were told the specific gravity is 2.6 and the hardness was less than 2. So we start looking for candidates, and the first thing that comes to my mind when you hear calcium carbonate, the common thing would be calcite, and that is definitely a calcium carbonate. It does have a white streak. The specific gravity is in range, but the hardness is 3. And you can't really get that mixed up, because calcite is actually the defining mineral for a hardness of 3. And the friend of mine that gave me the sample is very knowledgeable in minerals, so he would not throw a monkey wrench into there with having calcite being a different hardness. So, plus it's a real common mineral, and he said this was not common, so that would rule that out. There are actually 2 other minerals with the same formula, and they're polymorphs. In other words, they have the same material but a different crystal structure. And argonite is actually an orthorhombic crystal system, and the vaterite is actually a hexagonal crystal system, while the calcite is trigonal. But once again, everything matches up except the specific gravity of argonite is a little high, but the hardness on those do not match what we were told for the mineral sample. My uncertainty about magnesium leads me to think that it might have magnesium in there also, and that it might be dolomite, which is a calcium magnesium carbonate. So it does have the calcium, it is a carbonate, but the specific gravity and the hardness are a little bit too high also for that. So at this point, I'm looking at maybe some of those trace minerals, like that might be an anchorite. So that has calcium with possibly iron, magnesium, and manganese in it. It has the problem of being too high in hardness and specific gravity. There's also a material called galusite, which has calcium, and it's a carbonate, but it also has sodium, which could be possible too, because specific gravity is actually too low and the hardness is slightly too high. So that's kind of close, but doesn't seem to fit the bill perfectly. Now we're getting desperate, and I'm looking through all my books, and I'm looking for things that might be other carbonates. And there's magnesite, which is magnesium. There's siderite, which is an iron carbonate. And there's this trona, which is a sodium material. So all those are carbonates, but the hardnesses don't match, and nor do they have calcium, which I think is definitely there. So those don't work. Well, I'm really scratching my head at this point, and the only other thing I could think of is that maybe it's a marble or limestone, and those aren't minerals. The specific gravity and hardnesses of those aren't really published because they probably vary quite a bit depending on how they were formed. I went through all my books, including the book that has the tables with the 1,500 different minerals in it, and I didn't find anything else that even, came close. At this point I was really stumped, and I thought that was pretty much going to be the end of it with the big question mark. But I did go online and I looked at a big listing of carbonate minerals, and I found one other that is not in any of my books at all, and that was huntite. And that's a magnesium calcium carbonate. Looking at the properties, it does have calcium, it is a carbonate, it does have a white streak. The specific gravity is really close at 2.7 from the source that I looked at, and the hardness was between 1 and 2. So that seems to fit everything. The only thing I'm surprised at is if you look at the formula, it has 3 times the magnesium as calcium in it. I'm not surprised that there could be magnesium in it, but I would be surprised that magnesium is 3 times that of calcium. Now what I did do is when I did the testing of the calcium and I precipitated it out as an oxalate, I took the filtrate that was left over and did a test with the Chrome black tea and got a strong positive. But I didn't really mention it because I didn't know if I'm really precipitating out all the calcium and I'm just seeing leftover calcium, or whether it was truly magnesium there. I have a lot of work to do with my magnesium testing, but I'm going to go with that. My guess is going to be huntite, and if it's not that, I have no further guess. So well, there's good news and there's bad news. The good news is I came up with a possible candidate for the mineral. The bad news is I don't know if I'm right or not. So I'm going to let my friend watch the video, and you'll have to check back and look in the comments, and there'll be some information there to let you know if I was right or wrong. If you beat me to it and have some better ideas on what it might be, please comment with that also. Another piece of information too was the microscope. The mineral is described as being chalky, and that was definitely a chalky appearance under the microscope. Anyways, that huntite sounds like an interesting mineral. It's not in any of my references, and it wasn't presented as a mineral until 1953 in a paper written by a gentleman named George Faust. He said it was probably already discovered, but was discounted as either impurities in a manganese carbonate or something like that. And what's also interesting is there's references to a mineral back as far as like 1798, referring to a mineral called conite, C-O-N-I-T-E. And that they found had the exact identical composition as this huntite, but they never really made it an official mineral because there were a bunch of references to it and just some general information and general locations, but nothing specific, no specific location that they can go back and look for the stuff. So it was never really made into official mineral. So 1953 was when it came to the surface or resurfaced as a mineral. Once again, I don't know if I'm right, but that's the one I'm going with. Thank you for watching this very long video. Keep tuned to the comments to find out what this material really is. And happy rockin' mineral identification!